Okay, so we're back. And we said that in order to solve our second order linear homogeneous differential equation, we need a fundamental set of solutions. In other words, we need to find two functions for the second order such that the Wronskian is not equal to 0. Good. And so, by the way, just to give you a little bit of a lemma here, if we have ay double prime plus by prime plus cy equals 0, where we have r1 and r2 solves the characteristic equation ar squared plus br plus c equals 0. Now remember what the condition was for that? B squared minus 4ac is greater than 0. Then y1 equals e to the r1t and y2 equals e to the r2t form a fundamental set of solutions. Good. And so therefore we can solve, or we can write the entire family of solutions to this differential equation as c1 y1 plus c2 y2. Good. All right. Now, suppose I have a numerical solver, right? I have a numerical solver like Wolfram Alpha or something, and I can plug in my coefficients to my second order differential equation, and all I need to do is specify the initial conditions. Well, suppose, geez, my writing is getting terrible tonight, that y1 and y2 are solutions to, see if I can get my hand, okay, solutions to y double prime plus p of t times y prime plus q of t times y equals 0, where y1 solves the dE with y of t0 equals 1, y prime of t0 equals 0, and y2 solves the initial values, or solves the differential equation with initial values y of t0 equals 0 and y prime of t0 equals 1. Then y1 and y2 form a fundamental set of solutions. Good. Now you might wonder where these numbers came from. Are these magical numbers? That somehow everything works nicely with these specific numbers? The answer is no. The idea is that we're setting these numbers up so that the Wronskian of y1 and y2 is equal to what? The Wronskian of y1 and y2 will be y1 of t0, right? y1 prime of t0, y2 of t0, y2 prime of t0. If you look to see what these initial conditions are, what we did was we set this up so that this is 1, this is 0, this is 0, oops, this is 0, and this is 1. So all we did here was just, we chose these numbers so that in order to force the Wronskian to be 1, which is not equal to 0. So here's the question. Do we have to use 1 and 0, 0 and 1? No. You can use any set of numbers so that the Wronskian is not equal to 0. Okay? So sometimes people read this theorem and they get kind of locked into this 1, 0, 0, 1. Don't worry about those. This is just given to you to guarantee the existence, or to guarantee that the Wronskian is not equal to 0. Okay? Good. All right. We're just about through with the theory now. The last big theorem that we want to talk about. So what we've done so far is just discuss the theory for how to construct a fundamental set and what the ideas are behind a fundamental set of solutions. What we want to talk about now is something called Abel's theorem. Okay, and so Abel's theorem is going to help us figure out if a set of solutions is going to form a fundamental set. It's actually going to help us see if a differential equation has a certain. Oh, let me not give it away. So let's just go ahead and take a look at this. We know that the Wronskian. I'm going to suppress my dependence on t here, but I know my Wronskian. Here's the Wronskian here, is going to be defined by, let's go ahead and write it down, y1, y2 prime. Now I'm thinking of this as being a function of t, not being a function of t0. So this is going to be specifically a function of t minus y1 prime y2. Right? Now, because this is a function of t, you can actually compute the derivative of your Wronskian, right? What would the derivative of your Wronskian be? Well, this would be y1. I'm going to put this in a specific order because I kind of know what's coming. Y2 double prime. I'm using the product rule here. Okay, so that's the derivative of the first part, minus y1 double prime y2 plus y1 prime y2 prime. Good. What do you notice about the derivatives? I think these y1, I think those cancel, right? We're left with y1, y2 double prime minus y1 double prime y2. Good. So again, this is all looking at the Wronskian as a function of time. All right. Now, what differential equation did y1 and y2 solve? Well, there are two solutions. We're going to assume that there are two solutions to the second order homogeneous differential equation. So therefore, if y1 is a solution, then y1 and y2 solutions to the differential equation means that y1 double prime plus p of t times, this is going to be a lot of algebra, but I think it's it has a nice payoff at the end, so be patient. Oops, I'm getting too close. y2 double prime plus p of t, y2 prime plus q of t times y2 equals 0. Good. Now, I'm going to take the top equation and I'm going to multiply it by y2. And I'm going to take the bottom equation, I'm going to multiply it by y1. Okay, and then I'm going to subtract the top from the bottom and add straight down. And I wonder why I'm going to do that. Do you see what the first term is going to be? y1, y2 double prime minus y1 double prime y2. Do you recognize that term? That's a big deal. Okay. I'm giving it away. P of t times y1 prime y2. Oops, that's a minus sign. Plus p of t times, where am I? Oh, I'm running out of space. y1, y2 prime. Okay, minus q of t times y1, y2 plus q of t times y1, y2. And then 0 plus 0 is 0. Good. Now, bringing all this together, hopefully I'm not writing too small. We get y1, y2 double prime minus y1 double prime y2 plus p of t times y1, y2 prime minus y1 prime y2. I think I've seen that expression before up here somewhere, equals 0. Notice that these cancel. Do you recognize this differential equation? It is a differential equation, dw dt plus, oh, this is exciting, dw dt plus p of t times w of t equals 0. This is a first order dE in w of t. All right. I wonder if you can solve that. Well, you could solve it. I should say it's also it's going to be, what is that called? Not only is it linear, first order linear dE, it's linear, but it's also separable, right? So can we solve that differential equation? I think we can. In fact, let me write down the differential equation again. We were working with dw dt plus p of t times w of t equals 0. The solution is going to be an arbitrary constant times e to the integral minus p of t dt. Okay. I guess I could put the minus sign out. Be careful here. Be careful here. This is the Wronskian. This is not the integrating factor, right? Because the integrating factor itself is what? E to the integral positive p of t dt, right? You have a plus sign for the integrating factor. This is the Wronskian. Wowee. So what have we just shown? We've just shown that if y1 and y2 solve y double prime plus p of t times y prime plus q of t times y equals 0, then the Wronskian between y1 and y2 at t can be written as c e to the minus integral p of t dt. Wow, why is this such a weird thing? Abel's theorem. Do you see what's going on here? Why this is such an amazing result? This Wronskian, does it depend on y1 and y2? No, it depends on p of t. Wow, that's weird. That's weird. That's really weird. Well, maybe not real weird. Okay, it's kind of weird. So that's Abel's theorem. Now see if y1 and y2 form a fundamental set, then c will not be equal to 0. Otherwise, when you're computing, your Wronskian, you're going to end up setting your c equal to 0. Okay, and so that's how you get the two functions. Like if y2 is just a constant multiple of y1, then you're going to end up having c equal to 0 when you're solving. Good. What else does this say? This has another important, really important result. Ooh, and I'm running way over time. Important result. The Wronskian is either always 0 when c equals 0, or never 0 when c is not equal to 0, on the interval on which the solution exists, right? Because this exponential function is never 0. And so if c is not 0, then this is never going to be 0. And then if c is 0, that's always 0. So that's another key issue, and I've run way out of time, so I've got to stop here. And in the next video, we'll explain more.